Hi, everybody. Welcome back to Dave's Math Channel. I'm your host, David Tear, and this is my continuing feature on the Math Lovers book. And I kind of screwed up this week. I usually, every Saturday, feature the biography of another famous mathematician throughout history. Well, I delayed this for 3 days. I was kind of sick the last few days, and I'm also preparing for a trip that I'm taking in less than a week. So I guess I've got a lot on my plate right now. But anyway, I am doing this today. So the next famous mathematician on my list, which are listed in the end of volume two, that's the green volume on this slide. I list 80 biographies of famous mathematicians throughout history chronologically. I'm up to the 36th and I'm almost halfway done. And that one is Augustin Louis Cauchy, and he lived from 1789 to 1857. I think he's something like the fourth or fifth consecutive French mathematician on my list, coincidentally. I guess there were a lot of great French mathematicians in the late 18th and early 19th century. I guess it was sort of a renaissance for them in math for some reason. But anyway, here's the page from my book on Augustin Louis Cauchy. And what he's best known for, he did a lot of different stuff. He did a lot of stuff I didn't even mention here. But he was not just a great mathematician, he was also a great physicist. He studied things like Fourier series, wavelets, elasticity, a lot of that. He also did a lot of work in real analysis, including Cauchy sequences and Cauchy convergence. But I think his greatest accomplishment was his study of complex functions, analytic functions in particular. And I think, in a lot of ways, he really kind of pioneered the whole subject of complex analysis. This was one of the first results he came up with concerning complex analysis. If f is an analytic function, and it turns out analytic functions are very restrictive functions. They're functions over a complex variable. If you don't understand this stuff, don't worry about it. It's a little bit of a complicated area of math. Um, analytic functions are very, very well behaved functions. They're really just, their definitions are just differentiable over complex argument. But that turns out to be a pretty restrictive, um, you know, um, uh, property for complex. It's not so much for real valued function, as for complex valued function it is very restricted. Fortunately, most of the functions we study in the sciences, at least analytic, at least complex valued functions are analytic because they're well behaved. And this is just one of his formulas. This is known as Cauchy's integral formula. And what's remarkable about complex valued functions, you don't really have to understand this formula that well, but basically what this formula is saying, you have some integral of a complex valued function f of z, and then you're integrating it over f of z over z minus a, where a is some constant, and this will tell you the value of f of a. Pretty amazing formula that this works. I think C has to be a closed contour for this to work. But there's something called Cauchy's integral theorem, which says if you just have any analytic function, completely analytic, no poles, so it's not what's called meromorphic, it's analytic completely over some region, and then we have a closed contour, which we're calling gamma, and we take the integral of f of z dz of this circle over the integral sign just means it's a closed curve we're integrating about. If you compute this integral, it's always equal to zero. Um, and he came up with, I think, an even better result called Cauchy's residue theory. This is used all the time in complex analysis. This is very useful in physics in particular. So here, this is a generalization of Cauchy's theorem. So if you have a function that's what's called meromorphic, meaning it's not really analytic everywhere, it's analytic almost everywhere, except for a finite number of poles. Those are just places where the function blows up, goes to infinity. And then you take a contour around some or all of those poles, then you're not in general going to get an answer that's zero, but you'll get an answer that you can compute in terms of these things called residues. And he actually came up with the whole concept of residues too. So you don't have to actually calculate an integral. This is a very easy calculation. You just calculate the residues of the function at the poles, and then you sum them all up, all the residues inside your contour, and that gives you the value of the integral. That's what's pretty amazing. So, and I've used this formula a lot. It's a very, very powerful theorem. If you don't understand it, don't worry about it. It's pretty advanced math, but I think it's really, really beautiful result. One of my favorite results that I know of in all of math. And I think, in my opinion, I think this result alone, maybe his whole, theory of analytic functions, which kind of culminates with this formula, I'd say that this probably puts Cauchy in the top 20 mathematicians of all time, at least in my opinion. Um, and Cauchy, I mean, there's no question he was a really great mathematician. I also heard he had a huge ego. When he came up with this theory, I think he even said that he didn't think that God could even done a better job than him. So, he may have been a really great mathematician. Unfortunately, I think his ego was pretty badly inflated. But I guess that happens if you're a one of a kind, um, you know, mathematician or another kind of big shot. But anyway, I guess that completes my profile of Augustin Louis Cauchy. So thank you for watching. Long live math, and I'll see you guys next time.